Bridging Mathematics, Trigonometry, Applications of Oblique Triangles. Again, I'm Engineer Brian J. Guzman, and I will be your lecturer for this particular topic. Okay, so we are done with the topic for applications of right triangles. This time we're discussing now oblique triangles. So we're going to refer back to the principles developed in solutions of oblique triangles to solve for worded problems, of course, involving oblique triangles. Okay, so this particular video is very similar to the previous one. So these are also the wordings or the phrases that I've included in the applications of right triangles. But this time, the only thing that will change, okay, is that we're going to use principles from solutions of oblique triangles. So we're not going to use anymore the 6 trigonometric functions, nor are we going to use the Pythagorean formula. What we're going to use now will be the law of sine or the sine law and the law of cosine or the cosine law. Okay, but as always or as usual, our goal is to first draw the diagram, identify the triangle, and then now use whatever formula is applicable. Okay, so without further ado, let's proceed with the examples for solutions or applications of oblique triangles. Okay, so this is also the previous examples or passages from applications of right triangles. Of course, we carry over the discussion from angle of elevation and angle of depression. Okay, so let's have example number 1. So on the right side here, we have our formulas. These are the law of sine, a law of sine, and a law of cosine. Okay, so example number 1. A vertical pole 12 feet high standing on sloping ground is braced by a wire, which extends from the top of the pole to a point on the ground 20 feet from the foot of the pole. If the pole subtends an angle of 30 degrees at the point where the wire reaches the ground, how long is the wire? So probably, okay, there is a wire there so that to prevent the pole from toppling or falling over. That's why there's a guy wire there that is now to secure the pole on the ground. Okay. However, this particular scenario is that our ground is now inclined. Okay, so there is now an incline between the point of observation or the wire, okay, towards the base of the pole. It is now inclined. Okay, so the pole is 12 feet high. So first, of course, we need to visualize the scenario. 12 feet high. Okay, so it's braced by a wire, okay, which extends to from the top of the pole to a point on the ground 20 feet from the foot of the pole. Now, particularly, what is this distance? Of course, this is now also the inclined distance from the foot of the pole. Right? Since the ground is inclined, the measured distance from it is also inclined. Okay, so this is now the inclined distance from the base of the pole to the position of the wire. So if the pole subtends, okay, or meaning this is no longer a line of angle of elevation from the horizontal. Okay, it's not. If the pole subtends an angle of 30 degrees at the point where the wire reaches the ground, okay, so how long is the wire? So subtending meaning what was the angle that was swept, okay, to look at the top of the pole from the ground. So imagine the rotation starting from here, the inclined angle or the inclined ground, and then looking up and then sweeping up to the top of the pole. Okay, so this angle 30 degrees is not from horizontal on the ground, and because we don't also have any idea what the inclination of the ground is, so it's safe to say that this 30 degrees is between the wire and the inclined ground. Okay, so here is our scenario. And what do you see? Do you see a right triangle? None, correct? So we don't have a right triangle here, but we do have an oblique triangle. Okay, so if we connect the base or the wire at the ground towards along the inclined surface of the ground, correct, towards the foot of the pole, and then go up the vertical height of the pole, okay, and then from the top of the pole traverse the wire towards back to the ground, we're going to form this particular oblique triangle. So if we name our points, let's say this is point A, point B, the top of the pole, and then point C, okay, the foot of the pole. Let's incorporate the angles and distances. So this is 30 degrees, therefore angle A is 30 degrees, okay. Height of the pole, that is 12, therefore the side A is 12 feet, okay. And then the length of the position of the wire from the ground towards the foot of the pole, okay, along the inclined surface of the ground is 20 feet. That is actually your side B, because it's opposite our B. Okay. Now, if you want to use in other letters, it's up to you. You can make this your, or if you want to interchange the letters, you can make this your A, you can make this your B, you can make this your C. But you need to be sure that you know how to define which side corresponds to which angle. Okay, so in our particular triangle, in my triangle, A is 30 degrees, side A is 12, side B is 20. Okay, now what is being asked again? How long is the wire? So in our particular triangle, what is the wire? The wire is actually side C, correct? Because it's the one opposite angle C. So how long is this wire? So if you recall, for the solutions of oblique triangles, we have 4 cases. Cases 1, 2, 3, and 4. The cases vary depending on what is given on the problem. And in this particular problem, we are given what? An angle and 2 sides. This is actually case 2. For case 2, we solve it exclusively using the law of sine. So we're going to use the law of sine. Here it is, correct? So how do we solve now our particular length of the wire? So length of the wire is C, correct? So side C. So if we have the sine law here, so we're given A, angle A and side A. So if we have C, side C over sine angle C equal to A over sine A, this becomes, okay, solving for C only, 12 times sine C over sine 30 degrees. Meaning if you want to solve for the length of the wire, okay, that is C, we need angle C, and we don't have angle C. Well, since this is a triangle, correct? We know that for a triangle, the summation of the measures of the angles of a triangle is always 180 degrees. Okay? So C is equal to 180 minus A, that is 30 degrees minus B. But again, we cannot solve for C because we do not have angle B. So it turns out, if you want to solve side C, you need to solve angle C. If you want to solve angle C, you need to solve angle B. And how do we solve angle B? So I think we can also solve it using the law of sine for this time if we take the reciprocal. Okay? So here if we use sine angle B over B is equal to sine angle A over A. Okay? Solving for sine B, the cross multiplying B here, that is B sine angle A over A. Do we have side B? Yes, side B is 20. Do we have sine angle A? Yes, angle A is 30. Do we have side A? Yes, side A is 12. So input our known values here and take inverse sine in your calculator, shift sine, correct? 20 sine 30 degrees all over 12. If you compute this properly, you should get 56.443 degrees, or if you convert this into a sexagesimal symbol, that is 56 degrees 27, sorry, this is minutes. This should not be degrees. This should be 56 degrees 27 minutes. That should be a, you call that apostrophe. Apostrophe ba yun? So yeah, this should be minutes. Okay? So since we now have the angle for B, we can now solve for angle C. So angle C turns out is 180 degrees minus 30 degrees minus angle B, 56 degrees 27 minutes. And it turns out angle C, okay, is 93 degrees 33 minutes. Okay, so angle C is 93 degrees 33 minutes. That is the angle here, from the vertical pole towards the inclined ground. So you might be wondering, sir, I thought the pole is always vertical. Yes. Why did it not make a 90-degree angle? Because the ground is not horizontal. Okay, so it's a bit inclined 3 degrees, 33 minutes. Now, if you have angle C, what is our goal? Solve for side C. So input angle C here, we get this particular equation. So sine 93 degrees, 33 minutes times 12 over sine 30 degrees. C, it turns out the length of the wire is now 23.954 feet. Okay, so that is the length of our wire. This time for oblique, we are using oblique triangles. We are using the law of sines or cosines. Okay, so I hope that was clear. So if we use now law of cosine. So a while ago, our solution was mainly focused on the law of sine, right? How about if we use the law of cosine? Because if we're looking for, let's say, side C, there is also a formula, correct, that gives you side C using the law of cosine. This is this particular formula. C is equal to the square root of A squared plus B squared minus 2AB cosine C. Now, in this particular formula, what do we know? Do we have, okay, side A? Yes, it's 12. Do we have side B? Yes, it's 20. Do we have C? Angle C? No, not again. Not yet. Correct. So again, for us to solve C here, we must, or side C here, we must solve for angle C. And we're going to have the same solution as we did a while ago, which is now C is equal to 180 minus A minus B, and then B we should also be solved the same way using sine law. Okay, we'll get again the angle of C, which is 93 degrees, 33 minutes. Now, let's try to solve for side C using this particular formula, not the sine law. Okay, so let's see if the same answer will be yielded, and yes, it will be. Okay, but if I were you, I think I'll use the sine law, because the law of sine was much simpler than this. This one is a bit, especially if you don't want to memorize the cosine law. Okay, so this is a bit complicated. But this just shows you that the same problem can be solved in many ways as long as you know how to properly use the formulas. Okay, so this was two solutions for the same problem, problem number 1. Okay. Okay, let's have example number 2. Now, a ladder 20 feet long is set with one end at a horizontal distance of 7 feet from a sloping wall. The other end is the ladder reaches 15 feet up the face of the wall. What angle does the wall makes with the ladder? Okay, so what angle does the wall makes with the ladder? Okay, so this is a bit different from our previous problem. For the previous problem, the inclined or the sloping one was the ground, correct? The pole was vertical, but this one, the ground was horizontal. The ground is horizontal, and then the wall is the one that is inclined. Okay, so if you place a ladder that is 20 feet long here, okay, what is now the angle that the ladder makes with the wall? Okay, first of all, we need to extract a triangle here. Is there a right triangle somewhere? None, correct? Because the wall is inclined. If the wall was not inclined, let's say vertical, that's a right triangle, because this is not a, because this will be 90 degrees, but it's not. Okay, we do know that the ladder is 20 feet long, so this particular distance from this part of the wall to this ground, okay, on the ladder is 20 feet, right? What else do we know? Well, we know that the distance of the foot of the ladder to the wall is 7 feet on the horizontal ground. Okay. Also, the other end of the ladder reaches 15 feet up the inclined wall. So this is now 15 feet. Okay. So do you see the oblique triangle? So the oblique triangle is from here, from the foot of the ladder towards the inclined wall, up, okay, the inclined wall towards the top of the ladder, and then back again to the foot of the ladder. So if we draw the oblique triangle here, that is this one. Okay. So let's try to name it. Let's make this point A, point B, and then point C, and incorporate the given distances. So if this is A, side A is 15. If this is B, side B is 7. If this is C, side C is 20 degrees. Okay, this is an oblique triangle wherein we are given 3 sides. So what case is that? That is now case 4, right? So case 4 is where you have 3 given sides of an oblique triangle. How do we solve this particular example? Well, we use the cosine law, or the law of cosines for angles. Okay, so what angle are we after? That's the angle between the ladder and the wall. Okay, that is this angle, or angle B. Angle A is the angle between the ground and the ladder, and meanwhile angle C is the angle between the ground and the wall. We want the angle between the wall and the ladder. So this is the wall and this is the ladder. So the angle that we're after for is B. So we're going to use formula B, this one. So inverse cosine of A squared plus C squared minus B squared all over 2AC. Substitute the values of A, C, and B correctly, okay, take note, and solve for B. You'll get B as 16.26 degrees or 16 degrees 16 minutes. That is your answer for example number 2. Okay, so example number 3. Last example for oblique triangles. So a flagpole, 10 feet tall, stands on top of a building. So we have another flagpole, okay? From a point in the same horizontal plane with the base of the building, okay, the angles of elevation of the top and the bottom of the flagpole are 60 degrees and 50 degrees respectively. How high is the building? So this particular problem is very good because we're now going to combine the principles of oblique triangles and right triangles. Okay, so imagine a stationary point here wherein you're now observing a certain object on top of a building. Okay, so according to the problem, from this point, okay, there's no given distance from the building. Okay, you spot the top of the flagpole, you get an angle of 60 degrees. You spot the bottom of the flagpole or the top of the building, you get an angle of 50 degrees. Okay, if the flagpole is 10 feet tall, how high is the building? This one. Okay, how many triangles do you see? I think we have at most 3 triangles, but the useful ones we only have 2. Okay, let's start with the topic of our video, which is now oblique triangle. Do you see an oblique triangle? Okay, so I do see an oblique triangle. So that is now from the ground here. Okay, let's call it point A here. Then up, okay, here towards the top of the flagpole. Let's call it point B. And then down the height of the flagpole, let's call it point C. And then back on the ground. Okay, that is now the first triangle. Let's call it triangle ACB or ABC. Okay, let's try to identify now the properties of this particular triangle. Okay, what is now angle A for this particular triangle? Notice that the angle from the horizontal, or the angle of elevation to the top of the flagpole is 10, and then the angle of elevation to the bottom of the flagpole is 50 degrees. But what is this particular angle? Of course, that is now the difference between, correct, 60 and 50, or that is now 10 degrees. Okay, that is now angle A. Opposite of angle A, you have the height of the flagpole, which is now 10, so that is now side A. Okay, how about this particular angle here? Let's call it angle B. I placed there 30 degrees. Why? Because I told you we have at most 3 triangles here. One oblique here, a right triangle here, and then another larger right triangle here. From the ground to the top of the flagpole to the base of the building, that is a larger right triangle. What is the angle of that right triangle? It has a 60 degree angle here. Therefore, its angle here is what? These 2 angles should be complementary, correct? So this angle should be 30 degrees. So this angle must be 30 degrees. So angle B is 30 degrees. Opposite angle B, okay, that should be side C. Let's name it D. Okay, so this is an arbitrary name. Okay, I'm just going to name it D. Okay, so side D. Now, we do have another triangle of importance, that is your right triangle, that includes now the height of the building. Okay, so from the ground here, let's call it point A, or let's adopt point A. Okay, towards the top of the building, let's adopt point C as well, so point C, and then back to the base of the building. Let's call this one, since we already used B, let's now try to use D. Okay, let's call it now D. So we're going to call this triangle ACD or triangle ADC. Okay, so on this particular triangle, what are given? Well, angle A in this triangle, okay, is 50 degrees, right? Side A in this triangle is the opposite of angle A, which is the height of your building. That's actually our unknown, right? And then this particular length, okay, the opposite of D, let's call it side D, is also present on the oblique triangle, right? So this D is present on the oblique triangle and on the right triangle. That's very important because that means we can use this particular length later on. Okay, but what do we want? We want the height of your building, which is present. Where is it present? Is it present on the oblique triangle or the right triangle? It's present on the right triangle. So looking at the right triangle from triangle ADC, okay, how do we solve for H? So let's use the 50 degree angle here. Okay, so we have the angle, the H is opposite, okay, and then we have D. So angle opposite hypotenuse. So angle opposite hypotenuse. So katawa, sine is equal to opposite over hypotenuse. So we're going to use sine. So sine 50 degrees is equal to opposite over hypotenuse D. Therefore, okay, sine is equal to H over D. Solving for H, that is D sine 50 degrees. So again, we cannot solve directly yet for our unknown H because we still have D, which is also an unknown. So where can we find the value of side D or the length D? Fortunately, D is present on the right triangle and on the oblique triangle. So looking now to the oblique triangle from your triangle ACB, how do we solve for D? Okay. So what are we going to use here? For the oblique triangle, we have angle A, its opposite side, which is side A, 10. We have angle B. Oh, it turns out that angle B's opposite is angle D. But supposedly correct, what do we call the opposite side of angle B? Side B. Therefore, we can say that side B is equal to D, actually. Right? So if we use the sine law for A and B, okay, we can replace B with D because they are the same. Okay, so using sine law, since A is given, then sine A is sine 10 degrees, B is your unknown D, and then sine B is sine 30 degrees. We can use this to solve for side D. And side D will give you, so following this particular formula, replacing B with D, okay, 10 sine 30 degrees all over sine 10 degrees, which makes your D, okay, 28.794 feet. Where are we going to use this one? We need this to solve for the height of the building. Okay, so H is equal to D, 28.794 sine 50. That gives you H equal to 22.057 feet. That is now the height of your building. So this is now a combination of oblique triangle and right triangles. So in reality, you can solve almost any type of problems already now, okay, now that we've discussed right triangles and oblique triangles. And I hope everything was clear. So if you have questions, you kindly send them in your or in your respective instructor's inbox, okay, in Canvas. That is it. Thank you. See you on the next one. Thank you.